Okay, so we just talked about ions, and now we're going to talk about compounds made with ions, and they're called appropriately ionic compounds. And what we find then is that ions do not form in a vacuum, and when they form, they'll help form these ionic compounds. But let's look for a second. Let's remind ourselves what kind of ions get to be formed. Let's see, in particular, we've got main group ions, transition metal ions, and polyatomic ions. But let's look just at our main groups for a minute here. And we see that we've got, generally speaking, on the left-hand side, and in the metals, we have a whole bunch of positively charged ion, and here's our little break here between metals and nonmetals. Okay, so we find that our nonmetals are usually negatively charged, negative 1, 2, 3, or 4, and our metals are generally positively charged. Do you guys see that? How that just happens? I hope. All right. And opposite charges, we find, well, what do opposite charges do? You've probably heard this before. Opposites do what? Attract. Opposites attract. So opposite charges, a positive charge, will be attracted to a negative charge. Two negative charges are not attracted to one another. And two positive charges are not attracted to one another, but a positive charge will be attracted to a negative charge. So for this reason, anytime we see a metal, even some of these down here, anytime we see a metal paired with a nonmetal, then for the purposes of this class, you're going to say, hey, that's an ionic compound, because metals like to make positive charges and nonmetals like to make negative charges, right? So anytime you see a metal combined with a nonmetal, you can say, hey, because metals usually like to make positive charges, nonmetals usually like to make negative charges, this is going to be an ionic type compound. So for example, sodium is a metal, chlorine is a metal. When I make a compound between sodium and chlorine, sorry, chlorine is a nonmetal. When I make a compound between the two, if you can recognize that's a metal, that's a nonmetal, then you can say with confidence, I'm pretty sure that's an ionic compound. You guys with me here? Okay, so the next question is, how exactly does this happen? How do we form this compound between sodium and chlorine, where they're normally, or they were originally, we can say neutral, and now sodium appears to have lost an electron and chlorine appears to have gained an electron? Well, let's look at it like this. Here we've got neutral sodium, and it has an electron it wants to get rid of, so it can be like the closest noble gas. And here we have neutral chlorine, and it would like to gain an electron, so it can be like its closest noble gas, okay? So what happens is sodium goes on KSL or Craigslist and makes a post under the free section. I've got this electron, I don't really need it anymore. If anybody would like to come pick it up, it's free to the first comer, first come, first serve. I would like to get rid of it. And chlorine is browsing KSL Craigslist because he wants an electron and he's heard that he could find them there. And he discovers that somebody makes a post. And what's even better is he finds that it's a recent post, so sodium might still have that electron. And she lives nearby, so he might be able to go get it. So he immediately calls up sodium and says, hey, I'd like your electron. Do you still have it? I can come get it right now. Is that okay? And sodium says, yeah, sure, come on over. Here's my address. And so chlorine goes over to sodium's house. And he goes up and he knocks on the door. And sodium opens the door and says, oh, it's you. Yeah, here's the electron. What do you think? And chlorine says, that's great. I'll take it. And he picks up the electron. And essentially, this is what happens. So sodium now has become sodium plus because it gave away this electron that's been removed. Chlorine has now gained that electron and become Cl minus. And as soon as this electron transfer occurs, as soon as sodium gives its electron to chlorine, they pass it off from one hand to another. Chlorine takes that electron, and then he looks up at sodium, and their eyes meet. And all of a sudden, it's like fate, attraction. How could I have not seen before how beautiful she is? And he asks her out to dinner, and then they, 10 years later, they're still talking, laughing about that day and how they met on KSL because she was getting rid of an electron. All right, does that make sense? You guys with me here? So now I have a sodium, and now I have a chloride, and all of a sudden, ooh, you're so attractive. So they're stuck together at that point. Now, so ions don't, the point of this story is that ions don't form in a vacuum. That when sodium loses an electron, it has to go somewhere. Sodium can't just kick it out the door. When chlorine gains an electron, it has to come from somewhere. It can't just pick it up out of the air. And so this happens when these two elements meet each other. And once they meet each other and exchange electrons, yes, I just came up with that story. Not just now, but a couple years ago, yes. But when they meet each other and exchange that electron, then all of a sudden they're so attracted to each other that they're stuck together. They're just stuck, okay? You guys following me here? Was that too cheesy, or will you actually remember this? I hope. I hope that's the idea of the story, is to make you remember it. Okay, good. All right. So the next thing you need to know about ionic compounds is look really closely at this. What is holding sodium chlorine together? Opposites attracting. They're charges, right? It's just this attractive force. The positive charge is attracted to the negative charge. They are so attracted to one another that they are stuck like glue. And they're going to be stuck like glue until, well, they think it's love, but it's really just attraction. It's not really love, it's lust. Okay? Because it's just, oh my gosh, he's so attractive. That's what sodium and chlorine are saying about each other. And so they're going to be stuck together either forever or until something more attractive comes along, which might not be forever in the end. Okay, so I call this actually a little bit of a high school relationship. Your hormones are running really high, and all of a sudden you're looking at a guy that's never been attracted before, and you're like, oh my gosh, he's so attractive. How did I miss it? And you're just, your attraction, it's all haywire and wonky. But your high school relationships don't always last forever. Sometimes they do. They don't always last forever because they will often break up when something more attractive comes along. All right. So let's talk about what might be more attractive to an ionic compound. We've got to talk about water. Is when you put sodium and chlorine in water, for reasons we'll get to in the next chapter, water has this kind of a structure like this. These are covalent bonds. And water has a partial negative on one side of the molecule and a partial positive on the other side of the molecule. Now this partial negative, it's not a full negative. It's not as attractive to the sodium as the full-on negative from the chlorine. This +1 plus -1 charge, these two charges are much more attractive than this +1 charge is to this partial minus charge. But that's not the case when we put the sodium chloride or the salt in a thing of water. Oh crap, this is a really crappy looking picture, like I've been calling. Split this up here. I'm going to copy and paste this picture from my lecture notes. When you put sodium chloride in water, or any other ionic compound for that matter, the issue isn't that one water molecule is more attractive than the other ion I was paired with. The issue is that I have millions of water molecules, and these millions of water molecules will collectively have enough pull to separate those ions. So here, partially positively charged hydrogens are surrounding the chloride, partially negatively charged oxygens are surrounding the sodium, and it's enough to pull them apart. So this is like I just took that high school relationship, this ionic compound relationship, and I put it on Temptation Island. And even if all the people on Temptation Island aren't necessarily as attractive as the person that I was with, well, the fact that I've got that many people that are interested all of a sudden makes me realize that the whole wide world is out there waiting for me. And so it's just really hard to stay together in those circumstances. Does that make sense? Kind of. This is a property of ionic compounds called dissociation. Because the two ions have disassociated from one another and are now associating with the water instead. So any ionic compound that will dissolve in water will actually be dissociated. You can't see it with your eyeballs because it's all dissolved and dissociated and makes a clear solution, but it's there. And one way that we can see that it's there is that any water solution with dissociated ions becomes an electrolyte. The definition of electrolyte is not something that rehydrates you after sports, although that's where you might recognize it the most. Definition of electrolyte is that it will conduct electricity. Ooh. And it conducts electricity because electricity is basically a stream of electrons. And these charges help that stream of electrons move through the water where they wouldn't normally do so. So, bottom line, ionic compounds, property of ionic compounds, they will dissociate in water. When they do dissociate in water, they completely split up. And they do so because the water is collectively more attractive than the other ion they were formerly paired with. And we can see the properties of that water, and that water becomes able to conduct electricity, and we call it an electrolyte. You guys with me so far? Now, electrolytes are also really important for rehydration purposes, right? And I'm not just talking about sports, but cholera and other illnesses where you lose a lot of fluids can be life-threatening, and the best treatment is administration of water with electrolytes in them. So this is a discussion idea that you could post about in the forums. Again, you don't have to post about any of these. These are just ideas if you find them interesting or don't know what else to post about. But look up cholera and its treatment regimen and what you can do and what the mortality rate is if you don't treat it versus if you do treat it, where it comes from. It's kind of, we don't think or hear about cholera so much in the US, but it's still a very big deal in some third world countries. And the flu, yeah, we could talk about both of those. Okay, excellent. Megan Garza is typing, and I want to make sure that I answer her question. On the telemetry floor? Tell me about the telemetry floor, Megan. What is telemetry here? A heart ward, okay. Yeah, because your electrolytes there include both sodium and potassium ions, right? Yes. And conductivity, all of your muscles receive their signals through electrical impulses too, right? Yes. Excellent. Yeah, you should post about that in the discussion forums. That's definitely directly applicable. I'm glad that you mentioned that. It's good. Heads up on that. Exactly. Monitor replace potassium and magnesium, I bet, because sodium will replace the potassium. Okay, excellent, good. I do want you guys to talk about that, but in the discussion forums. And now we're going to talk about forming ionic compounds. You can write a little KSL story about each of these, but to the shorthand, we just want to see if I say, you know, these two ions make a compound, what is that going to look like? We need to know how to do that kind of quickly and easily. And there's one big rule that we have to follow, and that is compounds are neutral. They have no charge. If I have a charge, I'm not a compound anymore. I am an ion. By definition, ions have a charge and compounds are neutral. So if I have more than one atom and I still have a charge, then I'm just a polyatomic ion. I'm still not a compound, I'm still an ion. So if we're going to form an ionic compound, I have to put my ions together in such a way that what remains is no charge. Okay, because if I still had a charge, it would still be attractive to other ions. It would still be an ion. And so this is pretty simple with molecules that are made of singly charged ions, like lithium, which has a charge of +1, combining with fluorine, which has a charge of -1. Well, that's really easy. All I need is one of each, and now I have an ionic compound where those charges have canceled and it's neutral. That makes sense. But what if I was trying to make a compound between lithium, which has a charge of +1, and oxygen, which has a charge of -2? What would I have to do then? Yeah, you're going to need 2 of these lithium ions for every 1 oxygen ion that I'm reacting with. Katie's exactly right. So my formula between this would have to be 2 lithium ions and 1 oxygen ion, and now this is a valid formula for the ionic compound made between lithium and oxygen. Okay. What if I was making a compound between magnesium, which is +2, and fluorine, which is -1? What would I have to do then? You'd have to add another fluoride. I'd have to add 2 of these, right, in order to make that work, so that my 2 1- charges would balance out the 1 + 2 charge. So together, I'm going to have a formula of MgF2, and that is a valid formula for a neutral ionic compound made from the magnesium and fluoride ions. Excellent. Okay, let's try something like nitrogen, which is -3, add barium, which is +2. Or, because this is going to bug me, between barium, which is +2, and nitrogen, which is -3. This gets kind of pokey. If I add another barium, that'll have a total charge of +4 against my charge here of -3. So we can't be done if we do that. Okay, Megan says, what if I have 2 more bariums for a total of 3 bariums, and 1 more nitrogen for a total of 2 nitrogens? Is that what you're saying? Okay, so if we did that, then we would have 3 times plus 2 for a total positive contribution of plus 6. And here we would have negative 3 times 2 for a total contribution of minus 6. That works. My charges will cancel. So I can put in a formula of Ba3N2. Yeah, we can do more. We can definitely do more. Hang on a second. Okay, what if we did, let's see, what if we did one between titanium that was plus 4 and oxygen that was minus 2? Megan says, are there any that won't work out? No, there are none that will not work out. Since you get to decide what numbers go on there, you can just make the numbers so that they do work out. Ah, Megan says, look, if I just have 2 of those, this gives me minus 4. That's enough to cancel out the plus 4, since those charges are the same, plus 4 and minus 4. Now I know this will be a neutral compound made between the titanium plus 4 ion and the oxygen ion. Watch out, Danny, don't put, when we're looking at the formula of an ionic compound, I want you guys to all notice this. The formula of the ionic compound never directly says what the charge was on the ion itself. So the Li2O doesn't say that lithium was plus 1, and it doesn't say that oxygen was minus 2. That's right. The MgF2 doesn't say that magnesium was plus 2, and it doesn't say the fluorine is minus 1. Now, part of the reason that it doesn't say is because the point of the compound is to tell me how many of each atom I have. Always the compound formula, and you had a question like this on your last test. The formula is asking how many of each type of atom I have. That's what it's looking for. It's not looking for charges. Second of all, the other reason it doesn't tell you is because you and I already know, based on what we learned about ions here, if I have oxygen in an ionic compound, you know that the charge on that oxygen is minus 2. I don't have to tell you that the charge on this oxygen is minus 2. You know it because either you memorized it or you've got the periodic table in front of you so you can look it up. Okay? I don't have to tell you that magnesium's plus 2 and fluorine's minus 1 because you know, hey look, here's magnesium, must be plus 2. Here's fluorine, must be minus 1. So that's given by definition in the fact that this is an ionic compound, and B, ionic compounds are made from ions. So C, you look at the periodic table and say, what ion charge does this element have? Good question. Okay, so there's basically 3 questions that you have to ask when you're doing these types of problems. They are, that's very small. Okay, number 1, what is the charge on the cation? Number 2, what is the charge on the anion? And then number 3, what is the lowest possible ratio of cations to anions to make the formula with a net charge of 0? I should clarify, a cation is an ion with a positive charge. An anion is an ion with a negative charge. You can remember which is which because the cation, that T, is a positive charge. That's how you remember. So this is exactly what I did. I said, here's my cation, here's my anion. How many of each did I need to make that? Here's my cation. Here's my anion. How many of each of these did I need to make a neutral formula? Here was my cation. Here was my anion. How many of each of these did I need to make a neutral formula? And so on and so forth. For some of these harder ones, like for instance the barium and nitrogen problem here, essentially it might help to look for the lowest common multiple of those two numbers, because the lowest common multiple will definitely be a charge that will work for you. Might not be the lowest numbers possible, but it's a good place to start if you're not sure where else to go. Here was the cation. Here was an anion. Additionally, sometimes this works and sometimes it doesn't, but here's another idea. Sometimes you could take the charge of each of these and put them as subscripts to the other side. So this was 1 plus 1 minus, so they're invisible ones, because if there's not a number there, you know it means 1, which is how you could take this 2 and put it on the lithium here. You could take this 2 and put it on the fluorine here. And that's how you can get that nitrogen needs 2 and barium has 3. Here's a case where it doesn't work, because that would give you Ti2O4, and then I should hope you could recognize, this is not the lowest possible ratio, 2 and 4. I could take it all the way down to 1 and 2. So that trick does not always work, but it sometimes does. And if you can see that your multiples are too high, then you could catch yourself there. Okay. You guys followed me? Do you want to do a couple more examples? Okay, well, let's actually go to the in-class activity sheet here. So this is section 3. For each pair of ions below, what's the ratio of ions which would be required to form a neutral compound? And then I would just give the formula. So I give you lithium 1 plus and chloride 1 plus, then you can tell me what the formula would be. So help me do this one and this one. Help me do those two. What would the formula be between lithium and chlorine? What would be the formula between that barium and hydroxide? Okay, Megan's with me. I only have a 1 plus and a 1 minus charge, so those charges automatically balance or cancel each other out. So my formula will be lithium LiCl. And excellent. Megan recognized that I'm going to need 2 of these things. Now here we have to be careful, because if I say BaOH2, it looks like I have 2 hydrogens but only 1 oxygen. So it doesn't look like I've added 2 hydroxide polyatomic ions. So Kylie is exactly right. In order to make sure that you know and I know that they are 2 hydroxide polyatomic ions and not anything else, then I'm going to put parentheses around there. Like we discovered in last chapter, this parentheses means that this 2 will multiply through, just like it does in math. So I've got 2 of that polyatomic ion attached to the barium. Okay. Now I want you guys to practice these on your own and come with these to class on Wednesday. Section 4 is the same thing, except that instead of telling you, hey, here's what your ion looks like, I'm making you take the extra step and you tell me what the ions look like. So calcium and oxygen, first tell me what the ions are, and then what the formula will be. And let's do magnesium and nitrate. Again, tell me what the ions are. So there were 3 steps, right? The steps were 1, what's the formula and charge for the cation? Number 2, what's the formula and charge for the anion? And then help me put them together, but don't skip a step. So let's do calcium and oxygen here. Looking for calcium and oxygen. Let's see. A periodic table. Here we go. I'm gonna Oh, I wanted to keep the periodic table. Just want to get rid of all this extraneous stuff. You can see. Where's calcium? Where's oxygen? What do they look like? Okay, hang on a second. Calcium is right. Let's see. Here's calcium. I came here because this has got the element names on them. So calcium's +2 because it's in group 2, because it wants to lose 2 to be like argon, the closest double gas. If here's oxygen, it's in group 6. What does it want to do? -2. It wants to gain 2 electrons to be just like neon. So here we discover that we're looking at a compound made with calcium, which is +2, and oxygen, which is -2. So then what's the lowest common ratio of these two things that would give us a charge of 0? Diana, Houston, Megan, you all have it. Ca, you just need one of each. And again, you don't have to say in that formula that calcium has a charge of +2 and oxygen has a charge of -2, because that's just given. When you know it's an ionic compound, then you know that the charge on calcium is +2, and you know the charge on oxygen is -2. That's by definition, basically. Okay, let's try magnesium and nitrate. Help me out here. What's the formula and charge on magnesium? It's the formula for nitrate and the charge on nitrate. You guys don't have your periodic tables in front of you. Let's see what we can find here. Anybody see magnesium out here? Yeah, here's magnesium. It's +2. We don't see nitrate though. Not finding nitrate on anywhere on this periodic table. That's because it's not on here. Nitrate is one of our polyatomic ions. Oh, which one is it? What does it look like? It's kind of cluttery. Unclutter it. Nitrate, right? Has got the 3 oxygens. Okay, so, we were right here, sorry. So we determined that magnesium was in group 2, so it's got a charge of +2, and that nitrate has a formula of NO3 with a charge of -1. Okay, good. So what is the best formula that I can get that will give me a neutral charge? Perfect, Megan. If I have 2 nitrates for every 1 magnesium, that should give me a neutral compound. And I have to make sure, because that's a polyatomic ion, that if I've got more than 1, I'm going to put it in parentheses so I know that there's 2 of that whole thing, right? Because if I didn't have parentheses, it might look like N1 nitrogen with 32 oxygens if I'm not careful, right? That would be terrible. That's not at all what we mean. Excellent. Okay. So you guys can do this. I know you guys are a little bit nervous about it, but I think as you sit down and start doing it, it's going to make more sense. So let's move on to the next section, which is doing this in reverse. Okay. That is to say, here, I give you the ions, and you make the ionic compound. And that worked because you knew what the charges on these ions were. You knew either because you were able to look it up in the periodic table, or you knew because you were able to look it up on your table of electronegativity values, or you knew because you memorized them like you will with the, table of polyatomic compounds. You will have those memorized before this next exam. So you know those, so it's easy to put this together. But what if I was making an ionic compound with ions that are transition metals? Things that I don't automatically know what the charge is. That's crazy. Or what if I was looking at an ionic compound that was made from a polyatomic ion that's not listed here? These are just the common ones, dude. There's lots more. Guaranteed, there's hundreds of them. You don't have to know them all. These are the ones you need to memorize. But if you see an unfamiliar one inside of a formula, well, it turns out, because you know the way that formulas are made, because you know they have to be neutral, you can use that information to deduce what the charge on your transition metal or on that unknown polyatomic ion used to be. Okay? So help me out here. If you see a compound that looks like this, or a compound that looks like this, I recognize that these are way out of your comfort zone, but we know enough to pick these apart, and I want you to do them with me and watch how we do this, okay? We know that this is an ionic compound because I have a metal and a nonmetal. That's ionic. That was our definition, right? And we can look at this and say, by the way, that's a terrible F. It looks like a T with a cross. We can look at this and say, hey, this is an ionic compound. I know, because it's a metal and a nonmetal. But this is crazy. This is a transition metal. I don't know anything about transition metals. Crap. Well, you do know something about oxygen. What do you know about oxygen in ionic compounds? It has a -2 charge. By definition, if oxygen is in an ionic compound, it's going to have a -2 charge. That's guaranteed. You can take that to the bank. Excellent. So you know something about oxygen, and you know something about the way compounds are made. They have to be neutral, a net charge of 0. I can use that information. If I have 3 oxygens in this compound and they each have a charge of -2, how many negative charges are the oxygen atoms contributing to this compound in total? -6. Okay, so that means that the iron ions in total must be contributing what kind of charge to this compound in order for it to be neutral? +6. Excellent. Now, we can see that there are, in fact, 2 iron ions in this compound. So if the 2 iron ions must have a total charge of +6, what must the charge on this iron, on one of those iron ions, be? Exactly. Exactly. Perfect. This is a compound made between iron in its +3 state and oxygen, which is -2. That would give you a formula of Fe2O3. So even though you don't automatically know what the charge on iron is, you can deduce it because you know what the charge on oxygen is and you know how these things come together. Okay? So I'm not necessarily always going to tell you what the charge on the transition metal is, but if I give you a formula like this, I do expect that you should be able to deduce that charge by going backwards, just like we did. Okay? We'll do a couple of examples, but next I want you to look at this guy. What is going on here? This is crazy. This is crazy. Look at all these atoms. Hey, wait a second. What should you think when you see a whole bunch of atoms together like this in an ionic compound? One thing you do know, this is a metal, therefore this is an ionic compound, yes. But what is this? What's this craziness? This is crazy, crazy, craziness. We have metal with nonmetal, so I know it's ionic compounds. But there's not just one atom there. What is that then? How would you define what this thing is? There's more than one atom. It's a cluster of atoms. What's another word for cluster of atoms? That must be an ion because it's in an ionic compound, so it has to have a charge. It's polyatomic ion! Exactly. Hey, there's a bunch of atoms. Looks like they probably have a charge because it's in an ionic compound. They must be a polyatomic ion. Excellent. Polyatomic ion of some sort. Now you're going to say, ooh, that's interesting. Where is it on my list of, it's not on my list of common polyatomic ions. Panic, panic, what do I do? You don't panic. Hang on a second. Calm down, people. What do you know about this one? Potassium. Potassium has a +1 charge. By definition, always +1. Excellent. And how many of these potassium ions do I have? I got 3 of them. 3 at +1 gives me a total charge contribution by the potassium of +3. Excellent. So let me look at this thing. Is there more than one, or do I just have one of these? You're asking yourself, how would I even know? Well, if there were more than one, it would be in parentheses, like we did on the other page. So there's just one. Just one. So what's the charge on this polyatomic ion then, in order for it to counteract the charge on the potassium ions? -3, perfect. So what we have here is a compound between potassium ions with a charge of +1 and whatever the heck this thing is, which has a charge of -3. I think that's citrate. Another biologically important polyatomic ion, but not one that I'm having you memorize. So this is how we separate these out. That's how we kind of go backwards from the original. So again, here I'm going to break this down to a 3-step process. What we did was ask ourselves which was the cation and which is the anion. And here's the clue. you might not have noticed, but we have followed this rule. Cations are always listed first. We always have the cations, or the positively charged ions, before the anions. And then, what do I know? On either the cation or the anion, here we knew what the cation was. Here we knew what the anion was. And then step 3, therefore, what did this charge have to be in order for this to be a neutral compound, by definition? So we look at our in-class activity sheet. That's what this next section is talking about, section 5. Determine the charge on each atomic or polyatomic ion for the ionic compounds listed. Each of these is guaranteed to have one ion you don't know, either a transition metal, like here's chromium, transition metal, scandium, transition metal, or a polyatomic ion that might not be listed on your table of polyatomic ions, like this guy, or this guy, okay? I want you to go through and practice these. Let's do this guy. Help me out here. Just for extra practice. I'm assuming you guys want a little bit of practice, right? We could do 2 problems before we move on to the next section. Tell me, what do we know about OSO4? What's my cation and what's my anion? Do I know either charge? What do I know? Oxygen is the nonmetal. Excellent. Okay, so we're going to say, try to draw a careful line. So the OS is my cation, and the oxygen is the anion, because the nonmetals is usually the anion. Excellent. And what's the charge on, do we know the charge on the osmium or the charge on the oxygen? Oxygen is, by definition, -2. So we know I have oxygen with a -2 charge. Okay, in that case, what's the charge on that osmium have to be in order for this to be a neutral compound? Kylie says +8, Megan says +2. Anybody else want to chime in? The oxygen is -2, that's true. But there are 4 oxygen atoms. Diana agrees with Kylie, it's +8. Good for you guys, you're exactly right. +8 for osmium. That's kind of weird, isn't it? +8? What the? It's because it's a transition metal. Don't be at all bothered by that. The formula tells you what it has to be. There are 4 oxygen ions. Each oxygen ion has a charge of -2. So there's a total of 8 negative charges in this compound. In order for it to be neutral, I have to have a total of 8 positive charges. And there's only 1 osmium, so it's stuck with all 8. Good. Let's try this guy here. Ca parentheses ClO3 close parentheses 2. What do we know? What's the cation? What's the anion? Calcium's the metal, and it has a charge of +2 because it's in group 2. Excellent work. So calcium's +2. And there's only 1 of them. So this other thing, whatever it is, ClO3, what kind of charge does it need to have? Hang on a second. It's kind of obscuring the. There's 1 calcium that has a charge of +2, and it's paired with 2 of these chlorate thingies. I think it's chloride. I don't know. You don't have to memorize it. But if the charge on this whole portion is +2, then the charge on this whole portion must be -2. And since there are 2 of them, then each of them must, as Kylie noted, have a charge of just -1. 2 times -1 gives me the -2 that will cancel out the +2 that came from the calcium. This is hard, isn't it? It's think of it like a puzzle, a logic puzzle, because that's essentially what it is. The charges do have to cancel, and we just have to use what we do know, in this case the calcium, in the last example the oxygen, to deduce what we didn't know. You guys are Sherlock Holmes, okay? Deduce deductive reasoning to determine. That's going to take practice, but you guys can do it. Okay, I'm going to pause this recording. We're going to come back and talk about how to name things. But this is as hard as the stuff that we just did right here. This is as hard as it gets for this chapter. Just needs practice, that's all.